Welcome to G Fun Facts Online. Take a deep breath. Now, what if I told you that simple act could be exposing you to an invisible cocktail of harmful substances? We often hear about poor air quality on the weather report, usually with a color-coded number called the Air Quality Index, or AQI. But what is that number really telling us? Today, we're taking a deep dive into the unseen atmosphere to decode the AQI and understand the science of the air we breathe every moment of our lives. The Air Quality Index is essentially a thermometer for air pollution. It's a standardized system that takes complex scientific data and turns it into a single, easy-to-understand number, usually on a scale from 0 to 500. The higher the number, the more polluted the air, and the greater the health risk. The idea wasn't born in a vacuum. Its origins trace back to public health crises, most notably the Great Smog of London in 1952. For 5 days, a thick, toxic smog choked the city, caused by a combination of cold weather, leading to more coal burning, and a weather pattern that trapped the pollution at ground level. This single event was responsible for an estimated 12,000 deaths and was a brutal wake-up call. It made it painfully clear that air pollution was a life-or-death issue, spurring governments into action and eventually leading to the creation of public-facing tools like the AQI, which the US EPA first released in 1999. So when you see an AQI value, what is it actually measuring? It's not just one thing. The index is calculated based on 5 major pollutants regulated under the Clean Air Act. The overall AQI number you see is determined by whichever of these 5 pollutants is at the highest, most dangerous level at that moment. Let's meet these 5 atmospheric adversaries. First up is ground-level ozone, or O3. You've probably heard of the ozone layer, which is good ozone high up in the stratosphere, protecting us from UV radiation. Ground-level ozone is the bad nearby stuff. It's the main ingredient in smog. It's not emitted directly, instead it's cooked up in the atmosphere. Sunlight and heat act on a mixture of nitrogen oxides and volatile organic compounds, pollutants that come from car exhaust, power plants, and industrial factories. This is why smog is often worse on hot, sunny days. Breathing ozone can cause coughing, throat irritation, and chest pain. It reduces lung function and can trigger severe asthma attacks. Children are especially at risk because their lungs are still developing. Next, we have particulate matter, or PM. This isn't a single substance, but a complex mixture of tiny solid particles and liquid droplets. We classify it by size. PM10 are particles 10 micrometers in diameter or smaller. To give you a sense of scale, a human hair is about 70 micrometers thick. These particles are small enough to get into your lungs. Then there's the real villain, PM 2.5. These particles are 2.5 micrometers or smaller, so tiny they can penetrate deep into your lungs and even enter your bloodstream. PM 2.5 comes from combustion, vehicle engines, power plants, wood burning, and wildfires. Because it can travel through the bloodstream, long-term exposure is linked to premature death from heart and lung disease, and it's even classified as a carcinogen, meaning it can cause lung cancer. Our third culprit is carbon monoxide, or CO. This is the silent killer, a colorless, odorless gas produced when fuels like gasoline or wood don't burn completely. The biggest outdoor source is vehicle exhaust. When you inhale Colorado, it enters your bloodstream and hijacks your red blood cells, reducing their ability to carry oxygen. This starves your heart, brain, and other vital organs of the oxygen they need to survive, leading to poisoning that can be fatal at high concentrations. Fourth is sulfur dioxide, or sulfur dioxide. This is a gas with a sharp, pungent smell, primarily produced by burning sulfur-containing fossil fuels like coal and oil in power plants and industrial facilities. It's a major irritant for the respiratory system and can make breathing difficult, especially for people with asthma. Environmentally, sulfur dioxide is a key ingredient in acid rain. When it mixes with water and other chemicals in the atmosphere, it forms sulfuric acid, which then rains down, damaging forests, lakes, and even buildings. And finally, number 5 is nitrogen dioxide, or nitrogen dioxide. This is a reddish-brown gas that's part of a group of reactive gases called nitrogen oxides. It forms from fuel burning in our cars, power plants, and factories. Breathing nitrogen dioxide can irritate your airways and make you more susceptible to respiratory infections. It's also a double whammy pollutant because it plays a crucial role in forming both ground-level ozone and fine particulate matter. So how do we know how much of this stuff is in the air? The backbone of our monitoring system is a network of ground-based stations. These stations use highly accurate, sophisticated instruments to continuously measure pollutant concentrations. But they can't be everywhere. That's where satellites come in. Satellites provide a global perspective, measuring pollutants across the entire column of the atmosphere. They can track the movement of pollution plumes from wildfires or industrial events over thousands of miles, filling in the gaps between ground stations. More recently, we've seen the rise of citizen science, powered by low-cost portable air quality sensors. While not as precise as the official equipment, these sensors empower communities to monitor their own local air, identify pollution hotspots, and advocate for change. All this data, from the ground, from space, and from citizens, is fed into powerful atmospheric models. These are computer programs that simulate the chemistry and physics of the atmosphere to forecast what air quality will be like tomorrow, which is how you get that AQI forecast in your weather app. While we've focused on the US EPA's AQI, countries around the world have their own systems. Canada's Air Quality Health Index focuses on the combined risk of 3 pollutants. The European Index has 6 categories from good to extremely poor. China and India have their own comprehensive indices that include additional pollutants like ammonia and lead. This global patchwork reflects different local priorities and pollution challenges. One of the most critical aspects of this story is the deep, tangled relationship between air quality and climate change. They are 2 sides of the same coin, largely driven by the same activity, burning fossil fuels. Many air pollutants like carbon dioxide, methane, and even ground-level ozone are also greenhouse gases that trap heat and warm the planet. At the same time, climate change makes air pollution worse. Higher temperatures accelerate the chemical reactions that create ozone, leading to more smog. Climate change also alters weather patterns, creating stagnant air that traps pollutants over cities. And of course, a hotter, drier climate leads to more frequent and intense wildfires, which release enormous plumes of particulate matter and other toxins into the air. The history of this struggle is filled with both cautionary tales and inspiring successes. The 1952 Great Smog of London was a tragedy that shocked the world into action, leading to the UK's Clean Air Act of 1956, a landmark piece of legislation. More recently, consider Beijing. For years, the city was synonymous with airpocalypse. But through an aggressive, multifaceted campaign, switching from coal to cleaner energy, implementing strict vehicle standards, and relocating polluting industries, Beijing has achieved a dramatic improvement. Between 2013 and 2022, the city cut its annual average PM 2.5 concentration by over 66%. And here in the US, Los Angeles has waged a long war against smog. Its geography, a basin that traps pollution, and its car-centric culture created a perfect storm. But through decades of strong policy and technological innovation, like the catalytic converter which converts harmful exhaust gases into less harmful ones, LA has drastically improved its air. These stories prove that change is possible. Unfortunately, the burden of air pollution is not shared equally. Children are more vulnerable because their lungs are still developing, they breathe more air relative to their body weight, and they play outdoors. The elderly are more susceptible because their bodies are less able to cope with environmental stress, and they are more likely to have pre-existing heart and lung conditions. Pregnant women are another sensitive group. Pollutants they inhale can cross the placenta and affect the developing fetus, leading to premature birth, low birth weight, and long-term health issues for the child. The global scale of this crisis is staggering. The World Health Organization reports that 99% of the world's population breathes air that exceeds its guideline limits. Ambient or outdoor air pollution is estimated to cause 4.2 million premature deaths every year. When you add in household air pollution, that number jumps to 6.7 million. Cardiovascular diseases, like heart attacks and strokes, are the leading cause of these deaths. So what's the path forward? The science of air quality and tools like the AQI have empowered us with knowledge. These case studies from London, Beijing, and Los Angeles show that with political will, smart policies, and public engagement, we can clean our air. The solutions involve transitioning to clean energy, promoting sustainable transport, and enforcing strict emission standards. As individuals, we can use the AQI to make informed decisions, like reducing strenuous outdoor activity on high pollution days, especially if you or your family members are in a sensitive group. We can also make choices to reduce our own pollution footprint. Ultimately, the quest for clean air is a shared responsibility. By understanding the invisible world around us, we can all contribute to a future where everyone, everywhere, has the fundamental right to breathe clean air. Thanks for tuning in to Fun Facts Online.